please make sure you go to the portal and print out the PowerPoint for the second half of 10.3. So in this section, we are going to begin verifying our trig identities using algebra and then a couple of identities to be able to say what happens on one side of the equation will eventually match what happens on the other side of the equation. And so our definition of an identity is that whatever we replace for x or for theta or for alpha, no matter what we plug in for that angle measurement, is true for any value, then our equation is true no matter what. So if we had, like thinking back to plain old regular algebra, if I had something like x plus 2 equals, no wait, let's make that 2x plus 2 equals 2 times x plus 1. From our fabulous algebra skills, we can see pretty quickly that I have the exact same thing on both sides of the equation. 2x plus 2 equals 2x plus 2. And our eventual statement for this would be all real numbers. I can plug anything, any value at all in for x on either side, and I would have a true statement. Well, this one up here, is an identity, because it's the same. We can plug anything in for x, and we would have a true statement on both sides. And we will be verifying identities, showing all the work that makes one side of the equation equal the other side of the equation, even if at the beginning the equations didn't look the same. So when we're trying to verify our identities, a couple things to keep in mind, or strategies as we try to work through. We're only going to work on one side of the equation as we go through this. And typically we pick the more complicated side to try to break that down and make it match the simpler side. We're going to use our algebra skills to help us break down the more complicated side. That might be factoring, it might be combining our fractions with a least common denominator. I'll talk about finding a conjugate. So we're using all of our algebra skills to make our expression look like something else. And then we'll use our identities. I talk about fundamental identities like putting everything in terms of sine or cosine, or the Pythagorean identities, those are the ones that involve squareds like sine squared and cosine squared, to see if that helps make our complicated side simpler. Now, since we're trying to make one side the same as the other side, we can only work on the left side or on the right side. I cannot try to balance my equations. I need to do all of my work to make the left side match the right side. I cannot multiply to both sides. I cannot add to both sides. I have to restrict myself to one side or the other side. So here are some of our fundamental identities. They should look fairly familiar to them. They're breaking everything down in terms of sine and cosine, tangent, and then the secant, cosecant, and cotangent. We've probably seen written as 1 over before. We probably haven't seen sine as 1 over cosecant too many times, but it is a reciprocal identity. The Pythagorean identities come from our sine squared plus cosine squared equals 1. And we can use that to help us build the next two. So if I wanted to take the tangent squared, I am going to break that down into terms of sine and cosine. And secant is 1 over cosine. So as I'm looking at this, I can vaguely see that cosine squared looks like a common denominator, but my term of 1 does not have a common denominator of cosine. So I need to turn that into cosine squared over cosine squared. So if you take a look at this revised statement here, it really looks like the sine squared plus cosine squared plus 1 equation. I see that right here. And then everything was divided by cosine squared. And so with that worked through and simplified, we come up with this tangent squared plus 1 equals secant squared. It's a completely different looking Pythagorean identity, but that's where it came from. And I bet if I work on this 1 plus cotangent squared equals cosecant squared, something similar is going to happen. So let's see, 1 plus cotangent is going to be cosine over sine, and cosecant is 1 over sine squared. So in this Pythagorean identity, it looks like I need to change my 1 over 1 into sine squared over sine squared. And this time around, when we took sine squared plus cosine squared equals 1 and divided by sine squared, we wound up getting the 1 plus cotangent squared equals cosecant squared. So that's how the two other Pythagorean identities came to exist. Your job is to recognize anytime you see a squared term, you should double check to see if it works with one of the Pythagorean identities. So now we need to use our the identities that we have to see if we can take our more complicated side and make it match our simpler side. So if I look at secant squared minus 1, that's making me think about the tangent, secant, and 1 identity. So I'm going to go refer back to that. So the original identity looks like this. But if I were to subtract 1 from both sides in my identity, I would find that the numerator over here would match my slight rearrangement. So I'm going to take secant squared theta minus 1 and call that tangent squared theta over secant squared theta. And then I'm going to break down what I see here, because that certainly doesn't match sine squared theta. I'm going to break that down into terms of sine and cosine. So I know tangent is sine over cosine, and there's my big division bar after the tangent, and secant is 1 over cosine squared theta. So now I have a fraction over a fraction, and I know that division is multiplying by the reciprocal, so I have sine squared theta over cosine squared theta times cosine squared theta over 1. When I do this, the cosines can cancel, and I have sine squared theta over 1, which pretty much equals the other side of my identity. And I have verified that the two sides do in fact match the same thing. Now, if you saw some other way to verify this, as you might have, there can be more than one way to verify this identity. So you might not have seen the tangent squared that I did. You might have seen, oh, well, secant squared goes into both of those. Okay, and secant over secant is 1, and 1 over secant is cosine. And we had some identity up there about sine squared plus cosine squared equals 1. So if I subtract cosine off, so 1 minus cosine squared is called sine squared theta. So sine squared theta equals sine squared theta. Well, there we go. Both sides equal the same thing. So now I've done two completely different ways of making sine squared theta equal sine squared theta. They're both correct. And that's what I mean down here by saying there's more than one way to verify an identity. Okay, so I'm not sure which of these is more complicated, the left side or the right side. So I'm going to start on the left side and try to make it match the right side. Now, I have an identity about sine squared, plus cosine squared equals 1. And I have to get rid of this cosine here. So I'm going to say that cosine equals 1 minus sine squared. And this problem does not use theta, it uses beta. So I'm going to take 1 minus sine squared beta and subtract off sine squared beta. And now I have two like terms, the sine squared beta. So if I can combine like terms, I will have two of them. And would you look at that? Now one side matches the other. All done. So in this one, we're not using theta either, we're using alpha. And I have two fractions on the more complicated side that I need to add together. And if I'm trying to add fractions, I need a common denominator. So in my common denominator, I have 1 minus sine alpha and 1 minus sine alpha. Oh wait, no, I have 1 minus and 1 plus. Okay, so in my first fraction, it's missing the 1 plus sine alpha. And my second fraction is missing the 1 minus. So I now have a common denominator, lovely as it is. And in my numerator here, I have 1 plus sine alpha and 1 minus sine alpha. So my sines canceled out. I now have 2. And in my denominator, I need to multiply these together. So I would have 1 minus, no, plus sine alpha minus sine alpha minus sine squared alpha. My sines are going to cancel. 2 over 1 minus sine squared alpha. Well, I vaguely recall 1 minus sine squared alpha as being known as cosine. And if we have divided by cosine, that's the same thing as secant. So cosine squared would give us secant squared, so we have 2 secant squared equals 2 secant squared. So we're done. So when I look at this, I see that I have the squareds, the tangent squared and the cosine squared, which leads me to believe that I could use those Pythagorean identities. And I know the tangent squared plus 1 gives me secant squared. Now, I'm not sure if I should distribute the secant squared into the cosine squared minus 1, or if I should do something with the cosine squared x minus 1, because it doesn't quite fit my Pythagorean identity. My identity originally is sine squared plus cosine squared equals 1. So if I want to get cosine squared minus 1, I'd have to bring the 1 over, and the sine has to go onto the other side, which makes it negative. which is not usually what we come up with. But as I look to what we're trying to obtain, there is a negative on that tangent. So that's kind of leading me to think that this is a good path to take. If you had not gone down this path and decided to FOIL, you would have made your problem bigger instead of starting to make the problem smaller. And so you would have made it more complicated instead of less complicated. What I have now is less complicated than what we started with. That's a good sign. Then I can take the fact that secant is 1 over cosine. Sine is in my numerator. So now I have sine over cosine, which is also known as tangent. And the left side matches the right. So in this problem, we can see that the left side is more complicated than the right side. And on the left-hand side, we have some tangents, cotangents, cosines. So our best strategy is probably to put everything in terms of sine and cosine, because there aren't any squareds involved for our Pythagorean identities. So tangent is sine over cosine. Cotangent is cosine over sine. And then big division bar. So if we look in the numerator there, pretty much a whole bunch of things canceled out, which leaves me with 1 over cosine. And wouldn't you know that 1 over cosine is also known as secant. And so secant equals secant. Same thing on both sides. We're good to go.